Hello everyone, welcome back to the channel. In this video lecture, we'll be solving this problem: find if path exists in graph or not, which is a Leetcode easy problem. In this problem, there is a bidirectional graph. So what is a bidirectional graph? A graph which has two-way edges. It has n vertices or nodes, and each vertex is labeled from 0 to n minus 1. The edges in the graph are represented in the form of 2D array, where each element in that 2D array is a pair of integers denoting a bidirectional edge between those vertices. So every vertex pair is connected by at most one edge, and there is no self edge for any node. So what do we have in this problem? We want to determine if there is a valid path that exists from vertex source to destination. So we are given edges and integers n, source and destination, representing the number of nodes, source node and the destination node. We have to return true if there is a valid path from the source to destination, or false otherwise. So let's see the constraints of the problem. The number of nodes may go up to 10 raised to the power 5, while the number of edges may also go up to 10 raised to the power 5. And the nodes are labeled from 0 to n minus 1 if there are n nodes. And node 2, and there is no self edge for any vertex. And there are also no duplicate edges. There's exactly one edge between each pair of vertices. So let's better understand the problem statement using an example. So here we have our exemplar test case, which has been taken from the problem statement itself. We have 3 nodes, and we know that for n nodes they are labeled from 0 to n minus 1. So 3 nodes will be labeled from 0 to 2, 0, 1, 2. We have source node as 0, which is this, and destination node as 2, which is this. We want to find if there is a path from 0 to 2. Let's see how we can see that. So you can see that there is a direct edge from 0 to 2. So we can start from 0, we just jump to 2. Hence the answer for this test case is true. There is one more path from 0 to 2, which is move from 0 to 1, then from 1 to 2. Hence there are total 2 paths for this particular test case. We have 2 paths to move from node number 0 to node number 2. Fine. So how we can solve this problem? This is a very easy problem. Let's try to build the solution for this problem. So let's take this example. We have source node as 0 and the destination node as 4. We want to start from the source node and we want to reach to the destination node using some set of edges and check if we can reach the destination node or not. So how do we do that? We know that we have some graph traversal algorithms like BFS and DFS. So we can use BFS or DFS to solve this problem. So there's simple graph traversal algorithms. What do we do in BFS? We start from our source vertex and we push its adjacent nodes into the queue. So in BFS, we traverse the nodes in a level-wise fashion. So first we explore the node number 0. Let's say it is at level number 0. Then we explore the nodes which are at level number 1 or one edge away from the source node. Let's call it level number 1. Similarly, we keep exploring the nodes, and whenever we reach the destination node, that means we have a path to move from the source node to the destination node, and we return true there. And first time we reach the destination node, then the path along which we have reached the destination node first is also the shortest path. But in the problem statement, we are not asked to retrieve or print the shortest path. We just want to check if we can reach the destination node. And whenever we find or encounter the destination node while performing our BFS, we just return true right from there. Fine. So similarly, we can also use depth first search, but in depth first search, we know that. So we can also use depth first search for performing the same task. We can start from source node. We can recursively traverse the vertices from 0 to 1, then to 3, then we backtrack to the previous nodes and explore other children. Whenever we reach the target node, we return true. So this is the second approach to solve this problem. Here I'm assuming that you're familiar with these algorithms. In this video lecture, I will be using BFS algorithm to solve this problem. Let's dry run our BFS for this particular test case. Okay, so this is my queue where I push the source node initially, which is node number 0. This is the back of the queue and this is the front of the queue, and this is my visited array, which will be used to check if a particular node is visited or not. So initially we have source node, which is 0, it is visited. Then I pop this node out of the queue and I explore its adjacent nodes, which is node number 1 and node number 2. So I mark them visited in this visited array and I push them into the queue. Then I pop the next front node from the queue, which is node number 1, and I explore its adjacent node, which is node number 3. So we mark node number 3 as visited and we push it into the queue. Okay, so then we pop node number 2 out of the queue and we explore its neighbor nodes, which is node number 4. So we mark it as visited and we push it into the queue. So here I check that node number 4 is encountered, which is same as the destination node. That means we have arrived at node number 4 along some path and hence it is reachable. So we return true right there and we break our while loop because I found my destination node and there's no meaning in running the BFS. So that's how the BFS algorithm works for this problem. And let's see the implementation of the idea explained here, which is just a plain BFS. So this is just a plain BFS. We have this valid path function which takes in the number of nodes, edges, source node and destination node. I declare a graph, so it will be used to create or generate the graph from the given edges. Then I generate my bidirectional graph. So I generate two-way edges here. Then I create a visited array or a seen array, which will be used to keep track of the visited nodes. I mark the source node as visited, so this is source node. Then I declare a queue and I push the source node into the queue. Then I run my while loop till the queue is not empty. I pop the front node from the queue and I check if the node which is present at the top of the queue is the destination node. If it is the case, then I return true. Otherwise, I explore its adjacent nodes, and for all the adjacent nodes which are not visited yet, I visit them and push them into the queue to explore them in the next iteration. Finally, if I do not find my destination node while running this BFS, that means there is no path to reach the destination node which starts from our source node. Hence, I return false at the end of the function because I haven't find any such valid path. Fine. So this is how the algorithm works. It is just a simple BFS. We can also solve this same problem using depth first search approach. Let's discuss the time and space complexity for the idea explained here. Okay, so this is the time and space complexity. The time complexity for the given implementation is big of n plus 1, where n represents the number of nodes, m represents the number of edges, while the space complexity is also big of n plus m, and the time complexity is same as the time complexity for running a BFS. Since we are exploring all the edges and all the nodes, that's why the time complexity is big of n plus m. While the space complexity is also big of n plus m because we use a queue data structure to store those nodes and we explore all the edges for each node. Fine. Let's see the code implementation of this. Okay, so this is my valid path function which takes in the number of nodes and the edges, the source node and the destination node. So I first declare my graph, which will be used to create the graph from the given set of edges and nodes. Then I generate my graph from the given edges array. So I simply iterate over the edges and create bidirectional. Then I declare my visited array of size n. Then I declare my visited array of size n and mark all the nodes as unvisited. Then I mark the source node as visited and I declare a queue as well. And I initialize this queue with the source node. Then I run my BFS search. Then I pop the front node from the queue and I check if this node is the destination node. If it is the case, then I return true. Otherwise, I move to the neighbor nodes and I push all the unseen nodes into the queue. So if I encounter a node which is not visited, I mark it as visited and I push it into the queue. Finally, if I do not arrive at the destination node while running this loop, I return false right at the end of this function. Fine. So this is the implementation of simple BFS algorithm. It checks if there is a valid path in the given graph from the source to destination. This is the implementation in C++. Let's see the implementation in other languages. So this is the implementation in Java and this is the implementation in Python language. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I'll solve this problem with disjoint set union in my next video. So stay tuned with me. I'll see you in the next video. Till then, take care. Bye bye.